Hello everyone, my name is Rajkumar and today I am going to discuss one of the most fundamental nucleophilic substitution reaction, that is SN1 reaction. It stands for unimolecular nucleophilic substitution reaction, that is unimolecular nucleophilic substitution reaction. What is the meaning of unimolecular? It means the rate determining step, that is RTS, will involves only one substrate. Only one substrate. That's why we call it as unimolecular. And the meaning of nucleophilic substitution is when a group or atom is replaced by some another group or atom, that is nucleophile, is known as nucleophilic substitution reaction. Let's write a general chemical reaction. General chemical reaction of SN1 reaction, which follows that when we treat alkyl halide with nucleophile which is electron rich in nature, this nucleophile is going to replace this X group and it will form RNU with the elimination of X minus. Since X is departing from the substrate, that's why we call it as leaving group. It looks like a simple reaction, but it is a complex reaction which involves two steps. It means we are discussing the reaction mechanism of this reaction. That is how the conversion is going to take place. We are discussing the reaction mechanism Rn. So to understand the reaction mechanism, let's consider example, that is hydrolysis of tertiary butyl chloride, which will give the tertiary butanol with the elimination of HCl in the presence of water. This conversion will involve two steps. First step is formation of carbocation through dissociation of CCl bond with the elimination of Cl minus. And the second step is the nucleophilic attack, that is here water is acting as a nucleophile. Nucleophilic attack on this carbocation, which will lead to the formation of tertiary butanol with the elimination of H plus. The first step is slowest step, that's why we call it as rate determining step. It is the slowest step, it means we call it as rate determining step. Why it is a slowest step? Because the stable alkyl halide is converting into unstable carbocation. And the second step is fast step. Why? Because the unstable carbocation is converting into tertiary butanol, which is a stable molecule. This is a fast step. By using first step, that is RDS step, we can write rate law expression which tells that rate is directly proportional to the concentration of substrate, that is Rx. Here R is tertiary butyl and X is chloride to the power 1. Here we have written 1. Why? Because it is a complex reaction which involves two steps, and each step is an elementary step, and we know that for elementary reaction molecularity, that is 1, is equal to its order. That's why we have written that 1. From here we can say that the rate of reaction does not depends on concentration of substrate, concentration of nucleophile. Now I am going to discuss the energy profile diagram of this chemical conversion. So to write the energy profile diagram, we have to draw the two coordinates. We have to draw energy profile diagram. To draw the energy profile diagram, we have to take two coordinates. First one is x coordinate and second one is y coordinate. X coordinate represent the progress of reaction. We represent it as PR, that is P for progress, R for reaction. And y coordinate contains represent the energy of a species that is involving in these two states. Since this substrate is a stable molecule and we are converting it into unstable species, it means we are giving some energy, and we have to keep the substrate above the origin because it is a stable molecule. That's why we kept this from the above the origin. Since we are providing the energy, it means the energy of substrate is going to increase as a stage is reached at which the bond between Rx is about to dissociate. This stage is known as transition state, and this stage will lead to the formation of carbocation, that is R+. This carbocation will react with nucleophile in second state and it will give the final product, which is ROH. Through a transition state, that is ROH. This transition state represents that the bond between ROH is about to form. This is the energy level of reactant and this is the energy level of product. Since by observing this diagram, we can say that the enthalpy of reaction is equal to energy of reactant, energy of product minus energy of reactant. Here the energy of product is low and energy of reactant is high. By observing this equation, we can say that the enthalpy of reaction will comes out to be negative, that is it will be less than 0. From here we can say that it is an exothermic process, exothermic reaction in which heat is released. Now I am going to discuss the factors which affect the SN1 reaction. Factors affecting the SN1 reaction. Factors affecting the SN1 reaction. So the first factor is the stability of carbocation. Stability of carbocation. The rate of reaction of the rate is directly proportional to the stability of carbocation. Stability of carbocation. It means more stable the carbocation, more will be the rate. Let's see with an example. Hydrolysis of tertiary alkyl chloride, secondary alkyl chloride and primary alkyl chloride. In first step of hydrolysis, this will give tertiary carbocation, this will give secondary carbocation and this will give primary carbocation. Here the tertiary carbocation is stabilized by 9 hydrogen, that is 9 alpha hydrogen, which is adjacent to this carbocation through hyperconjugation. This secondary carbocation is stabilized by 6 hydrogen atom. through hyperconjugation, and primary carbocation will stabilize with 3 hydrogen through hyperconjugation. From here we can say that the tertiary carbocation is more stable than secondary, and secondary is more stable than primary. And we have already written that rate is directly proportional to stability of carbocation. It means the tertiary alkyl halide will give more rate towards hydrolysis than secondary, and secondary will give more rate than primary. Let's consider one another example. The example is hydrolysis of cyclopropene chloride. Hydrolysis of cyclopropene chloride, hydrolysis of benzyl chloride, and hydrolysis of aryl chloride, that is phenyl chloride. So in first step it will give a secondary carbocation, or we can say that allylic carbocation. This will give benzylic carbocation, and this will give the carbocation which is present on the benzene ring. This is least stable because the carbocation present on the benzene ring. Now by saying these two, this is aromatic compound, or ion, because it follows the Huckel's rule, and this is benzylic carbocation. Now the aromatic carbocation is more stable than the benzylic carbocation, and benzylic carbocation is more stable than this arylic carbocation. By saying this, we can say that the hydrolysis of cyclopropene chloride will be more than benzyl chloride, and benzyl chloride has more rate than the aryl chloride. Now the next factor that we are going to see is leaving group. How the leaving group is going to influence the rate of reaction, that is the rate of SN1 reaction. Second factor, leaving group. The rate is directly proportional to the leaving ability. And leaving ability is directly proportional to the stability of anionic species, that is stability of leaving group after dissociation. Let's see with an example. Hydrolysis of tertiary iodide and hydrolysis of tertiary bromide, hydrolysis of tertiary chloride. The first step of hydrolysis will give tertiary carbocation, that is tertiary carbocation along with iodide ion, tertiary carbocation along with bromide ion, and the third alkyl chloride will give tertiary carbocation along with chloride ion. We know that the iodide ion is more stable than bromide, and bromide is more stable than chloride, because as size increases, stability is going to increase it. So we can write that stability of I minus is more than Br minus, and Br minus is more stable than Cl minus. As I have already written that rate is directly proportional to the stability of X minus. It means the rate of hydrolysis rate of tertiary iodide is more than tertiary bromide, and tertiary bromide has more rate towards hydrolysis than tertiary chloride. Now I am going to see the next factor, which is solvent effect. That is third factor is solvent effect. What type of solvent we have to use in SN1 reaction, and how the solvent is going to stabilize the or influence the SN1 reaction. Solvent effect. Since we know that RDS step involves the formation of carbocation, that is positive charge, as well as carboanion. If we use polar protic solvent, let's say water, the lone pair of oxygen is going to coordinate with the carbocation. It will coordinate with carbocation. Oxygen will coordinate with carbocation, and oxygen will coordinate with carbocation. Oxygen will coordinate with carbocation. It will coordinate with carbocation. By saying this, we can say that the solvent molecule, that is water molecule, is forming a case in which carbocation is going to trap or stabilize through solvation. Same like carbocation, this anionic species is also going to stabilize through hydrogen bonding. The hydrogen atom of this polar protic solvent is going to coordinate with the negative charge through hydrogen bonding. Hydrogen atom will interact with negative ion. Hydrogen ion will interact with the negative ion. Hydrogen atom will interact with negative ion. By seeing this, you can say that the solvent, that is water, is forming a case in which anionic species is also going to trap. It means when we use a polar protic solvent, the rate of SN1 reaction is going to increase. Or we can say that in SN1 reaction, we have to use the polar protic solvent to increase the rate of hydrolysis or to increase the rate of solubilisis. Now the next factor is temperature. Since we have already know that factor 4, that SN1 reaction is an exothermic process, that is delta S will decreases, and for exothermic process we have to keep the temperature as low as possible to move the reaction in forward direction. It means for forward direction we have to keep the temperature as low as possible in exothermic process. What happens if we take high temperature? At high temperature, instead of moving in forward direction, the reaction will shift into backward direction. The reaction will shift in backward direction. That's why we have to keep the temperature as low as possible. Now we are going to discuss about stereochemistry of SN1 reaction. So to discuss the stereochemistry of SN1 reaction, we have to take a molecule which is chiral in nature. What is the meaning of chiral? Chiral is a molecule in which a carbon atom has 4 different groups. That is, a carbon atom is attached to 1 chlorine, 1 hydrogen, 1 methyl, which is present above the plane, and 1 phenyl, which is present below the plane. Now I am doing the hydrolysis of this chloride, that is alkyl chloride molecule. In first step, since we are studying the stereochemistry, that's why we have to write it on top. That is stereochemistry of SN1 reaction. In first step, it will form a carbocation where methyl group will present on above the plane, phenyl group below the plane, and it will form a carbocation. Now in second step, the water molecule, which is acting as a nucleophile, will attack from top or it will attack from bottom. It means it has 2 options to attack the carbocation. When the water molecule attack from top, this 3 group or atom is going to move in downward direction, and we get product like this, where methyl group is present above the plane and phenyl group is present below the plane. Now when the water molecule attack from bottom, these atom or group move in upward direction, that is, and we get this type of product where methyl group is present above the plane and phenyl group will present below the plane. Now to relate this product, we have to write its Fisher projection formula. What is Fisher projection formula? It consists of two lines, that is horizontal line which represents the group or atom that is pointing towards observer, and vertical line which represents that the group present on vertical line is pointing away from the observer. So to convert this product into Fisher, we have to see this molecule by a proper angle. Let's see. I am seeing this molecule by this angle. By seeing, we observe that the phenyl and methyl group is pointing towards observer. It means we have to write it on horizontal line, where methyl group present on horizontal line, methyl group present on right side, phenyl group on left side, OS on top and H on bottom. Similar to first, this we can convert second product into Fisher projection formula by seeing this angle. By seeing, we can observe that the methyl group is present on right side, phenyl group on left side, H on top and OH on bottom. Now we have to find its configuration. So to find its configuration, we have to assign the number according to their priority order. We have to give O as one priority order, methyl 2, phenyl 2, methyl 3 and hydrogen 4. It will move in anti-clockwise direction. It means it is S configuration. It has S configuration. And similar to first, we have to assign it 1, 2, 4, 3. It will move in clockwise direction. It means it is a R configuration. It has R configuration. Since water has equal probability to attack from top or from bottom, we get 50% S configuration and 50% R configuration. When we place a mirror image between these two products, we observe that these two products are mirror image to each other. It means these two products are enantiomer. It means we can say that this is S enantiomer, and this is R enantiomer. As we know that this is a 50% R enantiomer and 50% S enantiomer. It means we get a mixture of 50% R and 50% S enantiomer. And we know that the 50% enantiomeric mixture is known as racemic mixture. This racemic mixture is optically inactive. Why? Because the R enantiomer will rotate the plane polarized light by same magnitude as the S enantiomer will rotate. That's why we call it as racemic mixture. Now, by seeing this, we can say that the SN1 reaction is a racemization process. Or racemization reaction. That's it. Thank you.